Okay, so that's the advanced structural theories. Uh, Before the midterm exam, I talked about the static condensation. Okay, the static condensation actually it is not a very it is not a new problem or something very, very special, and I believe all of you have used this kind of the technique to solve the simultaneous equations. So if we have two equations, okay, so if we use the 1 plus 2, then we can get a new equations. Okay, originally we have two equations and with two unknowns, but if we combine these two equations, then we can get a new equation. Remember, this new equations is still a valid equations, and you can solve the equations to get your. If you can solve the equation to get the solution for the unknown, and it is the, the exact solution you like to get. However, right now in this equation, it is only one equation with one unknown. So if we use the coefficient matrix for these problems, it is a 2 by 2 coefficient matrix. But for these problems, it is a 1 by 1 coefficient matrix. So you can see the dimension of the coefficient matrix has already be a smaller one, and that's why we say it is a condensation. The condensation means that we can condense the stiffness matrix to be a smaller dimension. And for these equations, it is a valid equation, but it doesn't mean that we don't need to, we can forget about the unknown y. We can solve this equation to get the value of the x. But after you got the value of the x, you need to replace it back to the original equation. You can replace it into either one of these two. Then you can solve the unknown y. Okay, so even we can condense the coefficient matrix, we can reduce the number of the unknown, but it doesn't mean that the eliminated unknown, we can forget about it, and we still need to solve the eliminated unknown, and so usually we need to replace the solutions of the reduced unknowns back to the original equation to get this one. And what is the static condensation? The static means that it is the condensation is based on the static conditions. Okay, and what are the static conditions? For any conditions, they come from the something related to the force. Then we will call this kind of conditions, they are the static conditions. So if we can get some static conditions, then we can condense the stiffness matrix. Right now we are trying to solve the pin-connected problems. Okay, so for the plane frame problems, we could have the rigid joint. Also, it is possible we have the pin joint. And the pin joint means the members can rotate to each other, and at this joint it cannot resist or transfer any bending moment. So you cannot have the end bending moment for the beam. Also, you cannot have any bending moment at the top of the coil. Okay, so that's the pin connection. If we have, if we got pin connections, usually it means the rotations for the coil. So we have if we consider the coil line, so we have the theta. That's the joint 1, 2, 3, 4. So at the joint 2, we can say that's the joint 2 about the member 1. And also we have theta 2 for the member 2. Okay. So for the column, let's say it is the element 1. For the beam, let's say it is the element 2. And we need to define the rotation of the angle based on a center line of the member. So if we consider the element 1, at any point we can define the rotational angle. We can compare the original shape of the center line, also the bended center line. And if we define the tangents to both, then we can define the rotations between the original center line and the deformed center line. So for the column, we can define a center line. For the beam, we can define another center line. If it is a rigid joint, these two rotations must be same. Okay, that's the basic assumption for the rigid joint. But if we got a pin joint, then you do not have such kind of the behavior. The rotations for the column element at the top point will be same as the rotation for the beam element at the left end. These two rotations, they are different. Okay, so for such of the problems, we need to assume the unknowns. Okay. The other three joints, we do not have some kind of the pin connections, so we can just use only one rotations. And for the displacement for the nodal displacement, since the joint, it is assumed it can connect all the elements which is connected to this joint. So we can use only one set of the nodal displacements for each nodal point. And we need to assume the rotations theta 1, theta 3, and theta 4. Okay, since they are the rigid joint, so or you can say for the joint 1 and the joint 4, there is only one element connected to this joint. So the rotations of the joint theta 1 and the theta 4, it must be the rotations for the element 1 at the bottom point, and the theta 4 is the rotation for the element 3 at the bottom point. Okay, so there is no confuse. So we can say the assumed rotations only one. We need only one rotations for these three joints. But for the joint 2, we need to assume theta 2 1, theta 2 2. Okay, since there are two elements connected to this joint. Also, these two rotations, they are independent. They can be any value, and there's no need to be. You cannot derive the other rotations from another one. Okay, so we can solve the problems, but in this case, we need to use two rotations for the joint 2. Okay, but it is not a very good thing for the matrix structure analysis, since usually we will develop a program which can help us to solve the problems. But if you develop the program, you will like everything is the same, and you can use a common rule to consider all the problems. Okay, that's the typical thing for the solution method use the computer. So if at some joint we need to use more than 3 unknowns, it is not a very good thing for the program. Okay, so how can we eliminate these two rotations? Actually, we need eliminate only one of these two. Okay, so you can choose either one to eliminate. If we try to eliminate these rotations, then when you calculate the element stiffness, okay, remember usually we use the local coordinates when we derive the element stiffness matrix. So it is a 6x6 matrix. For this 6x6 matrix, we need to use the 6 degrees of freedom at the two end joints. And the U1, V1, theta 1, and I added the prime, so it means they are the local components at the joint 1. And also we need to use the U2 prime, V2 prime, and the theta 2 prime. And right now I can emphasize it is the theta 2 prime for the element 1. Okay, so you can develop a program like you can develop and you can calculate the element stiffness matrix, and it is a 6x6, 6x1, and this one is 6x1. But right now we know at the right hand side the related end force. Since it is a pin joint, so we know the end moment, the member end bending moment must be equal to 0. So we know at the top end of the member 1, we know the bending moment must be equal to 0. Okay, so that's the static conditions. Okay, that's the static condition. And then how we can try to use these conditions to condense the element stiffness matrix. Okay, that's the purpose we like to do. Okay, I think if you check for most of the reference book, you can see matrix operations to do the static condensation. Usually you will see that okay. First, we can make a partition. We can make a partition of the stiffness matrix. Also, we need to make a corresponding partition for the displacement vector. Also, we need to do the same partition for the force vector. Okay, and if you like to do the static condensation, you must have some static conditions. And in these derivations, he assumes the PB they are the known values. Okay. Remember, when you use the element stiffness matrix, usually at this time the elements in the force vector, usually you don't know the values right now. We know the applied loadings, so we know the external load applied to this joint, but we don't know how much shear will be any elements. So if we apply a force 100 tons, but you don't know if there are two elements connected to this joint, the applied force is equal to 100 tons. It could be 20 for element 1, 80 for the element 2, or it is possible 30 for the element 1, 70 for the element. The shear of the applied loadings be the member end force. So in most cases, when you use the element stiffness matrix, the elements in the force vector, the member end force, right now we don't know the values. Okay. However, if you solve the problems, if you solve the basic unknowns, if you finish all the procedures, solve the simultaneous equations, if you solve the unknown vectors, then you can go back to all the elements, and then you can calculate the corresponding member end force. But that's after you solve the basic unknowns. Usually we say that's the procedure you need to output the results. Okay, so when you solve all the basic unknowns, you like to output the results. At that step, you can say you can calculate the member end force for all the elements. But that's the procedure in the post-processor. But right now we are still in the processor. The processor is we are trying to calculate the element stiffness matrix. We need to assemble them into the global stiffness matrix, modify the boundary conditions, then we can solve the basic unknowns. But right now we don't know the elements. Okay. Only for some special case. And if you got a pin end at the member end, it is a special conditions. For these special conditions, we know the bending moment equal to 0. Okay, so in these derivations, we just use a symbol to represent for some elements in the member end force vector. You know their values. Okay, it could be more than one element. Okay, but it doesn't matter. For some elements, we know the the values of the memory and the force. Okay, so in this case, you can separate the original equations into two sets of the equations. Okay, after we made the partitions, then we can separate the original for the plane frame problems. It is a 6 by 6 matrix. So originally we got 6 equations, 6 unknowns. If we made the partitions, then we can separate the 6 equations into 2 parts. That's the first part. And for the second part, okay, right now we should emphasize only to the second set of the equations. Since only for the second set of the equations, we know the elements in the right-hand side vector. Since we know the PB, but usually we don't know the elements for the PA. Okay, since we know the values for the elements in the PB vector, okay, then we can use this set of equations to solve the UB. Okay, so so we can solve the UB vector from the second equation. Actually, you cannot say we can solve the UB vector, since if you check all the matrices on the right hand side, we know the KBB matrix. Okay, since after the input data, we know the Young's modulus, moment of inertia, shear area. We know all of these parameters, and also we can calculate the length of the element. Okay, so we know the EIAL of this element, so we can calculate all elements in the element stiffness matrix in real numbers. So all elements in this matrix, they are known. Okay, so for part of the element stiffness matrix, the KBB, they are also the known values. Also, we know the KBA. The KBA is also known. And since we are now considering the particular case, the special case, for example, the pin end problems. So we know the values of the PB. So we know the KBB, we know the PB, we know the KBA, but we don't know the UA. Okay, so it is not the solution for the UB. You can say we can express the unknown UB by some other unknowns UA. Okay, so it is only an expression for the UB. It is only an expression for the UB, but it is not a solution for the UB. Okay, since we don't know the values for the UA vector. Okay, so if we know the some static conditions, we can express UB as functions of some known values and functions of the UA, functions of UA. Then we can replace these expressions back to the first set of equations. Okay, so we can replace these expressions back to the first set of equations, then we can get this one. Or you can say which is the KAA minus okay. You should pay attention to the last equation. The last equations, usually we say that's the results for the condensed matrix. Since right now the matrix, after you calculate all the matrix in the parentheses, you will see for this matrix it is a smaller dimensions. Since originally, for example, for the plane frame problem, the original matrix it is a 6x6 matrix. If the UB contains 2 elements, UA contains 4 elements, then the dimension for the matrix in the parentheses will be a 4x4 matrix. Okay, the 4x4 matrix compared to the original 6x6 matrix, which is a smaller matrix, and usually we say it is a condensed matrix. It is a condensed matrix, and the UA contains 4x1, 4 elements, and if you calculate the elements for the right hand side, but you cannot solve the problem so far. You can calculate the condensed matrix, no problems. You can calculate the second term on the right hand side, no problem. But you don't know the values for the PA. Okay, remember when we calculate the element stiffness matrix, we have not solved the unknowns. So we don't know the shear from the joint loadings. So we don't know the values of the elements in the PA vector. Okay, so it is only an expressions, but in these expressions, it contains unknowns UA. Also, it contains unknowns of the PA. Okay, but it is a condensed element stiffness matrix. Since for this condensed matrix, which is a smaller dimension. Okay, if you check most of the reference book, you will see when the reference book discuss about the static condensation, you will see some kind of the derivation. But in my opinion, it is you can use these steps to explain what do you need to do. Okay, but in the actual calculation, it is not a very effective way to. It is not a very effective way to solve the static condensation problems. So the last time I remember I didn't even write this formula, but I think it is good for you to know there is an expressions to express why it is not very efficient. Since when we express this one, the known static conditions, not always the elements they are arranged for the last few. Okay, for example, this is the joint A, this is the joint B. In the fourth vector, we know the MA equal to 0. But the MA is the third element. It is the third element in the member end fourth vector. It is not the last one. For the previous example, the joint 1 to the joint 2, we know the M2 for the member M, for the element, for this element which is equal to 0. The M2 is the last element in the fourth vector. But in this example, we know the MA equal to 0, but the MA is the third element. Okay, so we could have many different cases. Not always the known conditions, they are arranged at the last. And for some students, after they learned this procedure, no matter what problem he needs to solve, he needs to rearrange the sequence of the unknowns to make the known conditions, they are the last few. But actually, you don't need to do this. So in this derivation, I will say it is good for you to understand the procedure you need to do. But in the actual calculations, I will not suggest you to follow such kind of the derivations. Okay, so I will take a break here, and I will continue it in the next time.